Hi everyone, my name is Carmina. I'll be your host for today's presentation, Challenges and Solutions of Advanced Automotive Radar System Design. Joining us today is Riccardo Giacometti, who is a Senior Application Engineer at Keysight Technologies. He is an Italian working in France, and he does a lot of bike riding, but hasn't won the yellow jersey yet. But there is always hope. Welcome, Riccardo. You now have the floor.
Good morning, everyone. So the agenda for this talk is going to be the following. So we're going to start with outlining the challenges of automotive radar system design. That will be followed by a quick description at the high level of the solution that is based on the Pathwave system design platform. It's also known as Systemvue. We're in the middle of the name transition at the moment. And then we'll follow up with the more details on MMIC system design, which will include a demo, and then a radar module system design, which also includes a demo, and finally vehicle level modeling, and also in this case we'll have a demo. So what are the challenges? Many engagements I've had with several players in the automotive radar industry all over Europe. These are some of the common themes that I have observed. So the basic building block is the MMIC, meaning the part that contains the transmitter receiver, and that needs to be both high performance and low cost. It also needs to be they need to be manufactured in very high volume, and it needs to be price is a very important factor in a very competitive market. The next level is integration of the MMIC with the Pcb and antennas to make the module, and that also provides several challenges. And then the system, both at the MMIC and the module level, needs to be tested in virtual scenarios even before the system is prototyped, and you can actually do actual drive testing, so it needs to be exercised, and the designer needs to be able to create some practical radar scenarios to see to evaluate the performance of the system design. So let's briefly talk about these Pathwave system design platform, and as I mentioned before, it's also known as Systemvue. So what are the key general capabilities? First of all, there are two types of simulation engines in there. One is a time domain engine, is data flow, and another one is specific for RF analysis, and it's a frequency domain engine, and it's called Hfss. The environment includes both baseband and RF building blocks of generic nature, and there is a specific automotive radar library, which we will see in more detail. In terms of interfacing with other languages or other modeling tools, there's a native interface with Matlab and C++, and also the ability to co-simulate with HDL in co-simulation type setup. We also have, or Systemvue has, direct links to RF design and test tools. So in terms of circuit designs, we're talking about Keysight ADS and Golden Gate, links with 3D EM simulators, and also links with measurement hardware. In this case, it's typically vector signal generator, vector signal analyzer, but also via S and X parameters with network analyzer. And there's a specific part of Systemvue that allows the accurate design of simple or complex phased array system. So in the case of a MIMO system, there will be a low complexity. We can look at it as a low complexity phased array, but given where the industry is going, the Systemvue has a solution that is able to address very complex phased array antennas. Let's now dive into an example of how to design an MMIC at the system design level. So let's take a very basic introduction to Systemvue. What you see here is on the left panel, you have the all the different objects there in this workspace. So you can see a schematic, there's a simulation control here, there's data sets, there's tables, there's graphs. So these are different elements on the left side. On the right side there's a library selector. So for this first example you see here, we'll be using the RF design library. But there's many others here, and the one we'll focus on later is this automotive radar part library. And here's the schematic. What we're modeling here is a single channel TX and RX system. So as you see here, this is the source that generates the signal. The signal is then split. This part goes into the TX branch. And the second part obviously goes to the RX, and there's a power amplifier. Then there's a block here that I'll describe shortly afterwards. And basically it models the PCB on the TX and the RX side, and the objective is to add insertion loss and also coupling. This block emulates the target, so there's a frequency shift here applied, and there's also an attenuation that's obviously depending on from distance. And then the receipt signal here it goes into this. It's actually the signal gets added to the signal gets added the thermal noise coming into the antenna, and given that the splitter is this is a physical simulator, so a power combiner has an insertion loss. And we need to compensate that using these amplifiers for compensation. So this is kind of a virtual signal injection, if you will. This is the LNA, this is the mixer, and then there's amplifier, a couple filters, and we go to the output here. So this is a fairly standard topology, and we're gonna next looking at what the results are. Obviously, all these models are we add noise effects, both thermal noise, phase noise, nonlinear models or elements like amplifiers and mixers. They have the nonlinearity effects added in. So this is a fairly accurate model of our MMIC, and where possible, every model can be replaced with either as parameters or in the case of linear blocks, or X parameters, or maybe AM, PM description, for example, for nonlinear elements like amplifiers. So once the schematic is set up, we run the simulation and visualize the basic results here. So as you can see, so this is the table that represents the essentially the path that the signal is going through. As you see here, it goes from the source to the TX amplifier, the PCB, then back into the PCB on the RX side, the LNA, the mixer, and the two filters, and the output. And you can observe here the evolution of this DCP column is the desired channel power, and it goes from, in dBm. And it goes from the input or the power the source is 10 dBm, and through its path to the target and back, you can see the value of this power, or the signal power. And on these two columns, you can see the thermal noise here, CMP, and phase noise as P and CP, and using these three numbers, the CNR, so the signal to noise ratio, is calculated. And this is obviously for whatever parameters were specified for the different elements of the block, and also for a certain distance. You can also visualize the same measurement graphically. So as you see here, on the x-axis, you have all the different elements in the path, in the predefined path from input to output, and then red trace is the desired channel power. And then in blue you have the addition of the thermal and phase noise, and again that's the progression throughout the structure. And finally the carrier to noise ratio, which you see displayed in dB. The scale is displayed here on the right side. Another visualization that is possible is the spectral, the wideband spectrum, and this is the spectrum at the output. So you see it goes from basically 0 to 100 megahertz, and you see the main signal. You see the harmonics, and you see thermal and phase noise, and the combined effect of the two together. So the last step of this presentation, this demo, is going to be it's going to consist of running a sweep. So as you see here, what we're doing here is we're running a system analysis, and then we're sweeping the distance here variable, and the list. So we're sweeping through a list that goes from 1 meter to 200 meter. So we can run the calculation here live. And then let's open this graph, and when it starts calculating, you'll see that the different sweeps will generate each one a plot, and each plot is going to have its phase and thermal noise associated. And this is a fairly complex plot that you probably want to analyze one trace at a time. But this is a way to show you kind of how the whole mechanics of the sweep works, and the different type of information that you can get on a plot, on a wideband plot, in a pretty fast simulation. Another way to look at this, there's another plot down here, and this is this is a table where you basically see the same thing, and this is maybe more intuitive, and you see the distance here going from 1 to 100 to 200 meters, and the corresponding CNR values for each of the distances, going from 26 dB down to a negative 0.357. Let's now transition to the design of the radar module. First, let's go back to the previous schematic, and there was one block that I said I was going to cover later, and that's the block you see here circled in red. So with that block, we take into account some of the module level effects at the Mmic simulation level. So let's briefly see what we can do there. The bottom left here, you can see the block zoomed in, and you can see that this is it's a 4-port block that represent the coupling between the TX. This is the output of the Mmic on one of the channels, and that's obviously representing PCB, and on this port we have the antenna output, and similarly on the RX side we have the antenna input here, and then we go all the way to the Mmic on the receive side. And what you see here is a simulation run on a board that you see here in the background, using Keysight RF Pro, which is the new ADS EM extraction environment, and you can see here the response, the S21, the S34. So there's two curves here, blue and green, that represent essentially the insertion loss on the TX and RX path. On this screen here, you can see basically the same thing, but now instead of insertion loss, we're actually looking at coupling. So these are this is the coupling here. You see the S13 and S24. These are the couplings between the TX and RX, and obviously there's both the insertion loss and the coupling effects. They play a big role in the system design or in the system analysis that we saw earlier. Similar analysis can be done at the physical level, that is using EM extraction, on the antenna side. So you see here a different board that has integrated antennas, and basically we're applying the same EM techniques to extract the radiation pattern for either for the whole antenna system, if the number of antennas is limited, or we can just extract a single the radiation pattern for a single element, and then scale it up using Systemvue. And this is how we can do it. So as you see here, this is a very simplified system here where you have some of the circuitry before the antenna. We have a coupler, we have an amplifier here, and this block here that you see, this array antenna block, this is where the response of the radiation pattern of a single element can be included, and can be scaled up to an arbitrary number of elements. So as you see here, you can point to to a pattern file. In this case, it's coming from EM Pro, which is Keysight 3D EM extraction platform. And you can then have several choices here in terms of attributing the same pattern to all elements or some elements, or custom mapping. You can rotate to reuse patterns placed in different geometries, and you can rotate around each of the three axes. I actually have more options in these other tabs here, but this is enough to kind of make the point there. That's in Systemvue you find a pretty comprehensive way to analyze MIMO systems, but phase array, more generally phase array systems, to a very high level of element counts and complexity, and also you have complete freedom in where physically you place the different elements in 3D space. So to complete the picture, once you set up the antenna system, then you have access to all the tools or the analysis functions that allow you to display complex radiation patterns like the one you see here for the TX and RX antenna of the example. Now we've looked at briefly the PCB and how to incorporate PCB and antenna effects into the analysis. Let's switch gears and talk about the library, the automotive library in Systemvue that we're going to use in the next example. And one important point is the system we're about to analyze, like a previous example, is going to use FMCW, but there's several waveforms that are being looked at for the next generations of systems. And one important point is that Systemvue has the flexibility to accommodate pretty much any waveform you can think of, and that's so there's different possibilities there. One very important part is the environment modeling, so the things like clutter, propagation loss, and then also there's micro Doppler analysis capabilities, and a lot of different ways to define targets in general. And then there's also a data processing part of the library that will help you with algorithms for detection of targets, also angle of arrival, and then some more sophisticated capabilities like compressed sensing and also target tracking. Let's now go into the second demo here. So here at the module level, and I'll give first an overview of what we're looking at here on the screen. So as you see, it's divided into different blocks. Let's start from here. So here you have the source modeling. This is in this case is an FMCW source. We'll see that in more detail. So the signal, we have a 77 gigahertz modulated signal coming out here, and it's distributed over 4 TX modules here, or transmitters. And each one, as you can see here, there's an input. This is basically it's phase modulation. So each of the 4 channels is phase modulated, chirp to chirp, and here is the signal going out to the 4 antennas. Those 4 signals, they get serialized here. They go through 4 parallel amplifiers, and this block here is the antenna block that it's very similar to what we've seen before, so it allows you to define the radiation pattern for each antenna, and basically from this the signal coming out of this block is the signal that is directed through the targets. This block here is an echo generator, and it's taking information coming from these blocks up here in this trajectory layer. So this is basically the definition of the movement of the ego plus however many targets you want to define, and we'll get into more detail. We'll see the details of that later. But once these targets are defined, and there are also the kinematic, how they move is defined, then this block calculates the echo that it's going towards the RX antenna. So this block is very similar to these TX block antenna block that we saw that was discussed earlier. And it's also a multi-element block, and the signal coming out of the antennas, again, is still parallel here. In this case, for receive antennas, is then deserialized by this block and sent to this 4-channel RX receiver. So this blocks here that you see is the analog front end, and then it goes into the digital signal processing. Here you have first FFT, second FFT, detection, CFAR, and then finally we get to this block, and again I'll go into more details about this, but this block is actually what does the final processing, where you can get range, velocity, and angle of arrival measurements out of this. Let's now get into the next level of detail. So let's zoom in here, and you see this is a block from the Automotive Radar library that you see here. These are all different parts in the library. This is the Automotive Radar FMCW, in this case CW, but with FM, because we have frequency modulation. You see here the delta frequency, in this case 250 megahertz, and then there is a TX up converter, that takes the signal up to 77 gigahertz, as you see here. And in this case, what can be done, and I'm not going to go into the next level, the next level of detail, but you can add also effects like for example, phase noise, amplitude noise. You can also add ramp, frequency ramp, nonlinearity of different types, and it can be completely arbitrary. It can be a measured data from your synthesizer or VCO, and then the signal, the 77 gigahertz signal, comes out of here and it goes into here. We can quickly maybe look at this, what's inside this box here, and you see this simple, it's a simple implementation. There's some noise density applied to it. There's this phase shifter that does the chirp to chirp phase modulation, and there's a power amp here where you can define the compression characteristics, and different effects, physical effects related to the behavior of the amplifier. So let's go back to the previous level here, and so there's 4 TX signals. They get, as I said before, they get serialized here. They go into another amplifier here, which it's actually there to represent the antenna gain. And then it goes into this antenna block here, and I want to quickly show you some of the details that you already saw some of that on the slides previously. And there are different possibilities in terms of placing the elements in space. There's also a custom option that allows you to specify in XYZ arbitrarily the location of each element here. Then in terms of the pattern, you can go with isotropic. You can also specify polarization, as you see here, and you can also use cosine type pattern. The option that it's typically used is this pattern file with data coming from EM simulation or measurements, and in this case you see there's option of getting the information directly from Keysight EM Pro 3D EM extraction environment, and you see some other options here in terms of other EM simulation environments here. And then you have the rotate option here, which when activated will give you other options in terms of rotating the pattern around the axis. So let's stop here, and then this is the next up in the chain here is the target echo generation. So this block, as you see here, it takes data through these inputs here from other parts of this schematic. So let's quickly, which is actually up here, and let's quickly go into the description of the kinematics of the system here. So as you see here, there's position of TX antenna, position of RX antenna, which are typically collocated, but so in Systemvue you can actually define the TX and RX to be located in different places. So it could be on the car. They're not necessarily located in the same spot. So you have that possibility. And as in this case, we define 3 targets, and you see these are supposed to represent position of truck in the right lane. You see a large RCS here. You see the XYZ position, velocity. There's actually also acceleration can be defined. There is each target can be defined with multiple scatterers, each subscatterer with its own RCS, and another detail here you see is you can actually operate a rotation around the 3 axes here, yaw, pitch, and roll, and that is also helps in analyzing more complex maneuvers like lane change and accelerating and braking, and what they do in terms of where the antenna is actually pointed exactly, and analyze those if you will second order effects accurately. So in this case we have 3 targets, and they're defined with the XYZ coordinates and vector velocity vectors. So we have a car in left lane, and we have a far car in the right lane, and that's those are the specific configuration here. But again, as I said before, you can define an arbitrary number of targets, and each of it with independent trajectories, which by the way can also be defined, can also be file based if you have a particular trajectory that you're interested in. This blocks down here, they make a transformation, and they calculate the relative position of the vehicles, both ego and targets, and with respect to each other, and all this information then gets sent to this block here, and that's the block that does the final calculation of what the echo looks like, and then sends it to the RX antenna block. I'm not going to open this up because it looks identical to the TX block, and then from here it goes into amplification again for the antenna gain on the RX side, and then the 4, in this case it's a 4x4 system, so the 4 channels get deserialized here and sent to the RX receiver. So the RX receiver in this case is modeled quite simply. By the way, what I showed before in terms of the more detailed MMIC architecture can be plugged in here directly. So in this case we use a simplified, this is a standard example in the product, so we use a somewhat simplified modeling here. So you see there's an IQ mixer type configuration, the LNA obviously, and there is in this case there will be some filtering probably, and there will be an ADC. In this case we just model the ADC through downsampling, but there's an ADC model that allows you to include more sophisticated effects of quantization, linearity, jitter, and things like that. So let's go back up to the top level here, and so the signals. This blocks essentially they do first and second FFT. So one possibility you have here, and I'll come back to this later, is to actually get the data at the output right here at the output of the A to D converter, and transform it into a data cube and do signal processing externally in, for example, Matlab or other signal processing languages or tools, or otherwise you can use the blocks from what is here the general algorithm design library here, blocks like we used here to do FFT and other digital signal processing functions. The library contains also the CFAR algorithms, as you see here: range FFT, Doppler FFT, then CFAR. And last point I wanted to show here is this block here you see is a Matlab scripting block, and you can define an arbitrary number of inputs and outputs. You can basically write your equations in Matlab, and there is if I right click here, you see there's an integrated Matlab scripting engine in Systemvue, which is included with a Systemvue license, or if you need, which obviously it supports a certain number of functions. If you need to use functions that are not included in the scripting engine, then you can switch to install Matlab and use a Matlab license, and you can switch to the let's say full Matlab installation and use it in co-simulation here. So as a result here, you get the angles, ranges, and velocities, which are you can find here in different tables. So you see here the angles for the 3 targets, for example. Same thing for ranges and velocities. And now let's close this windows here. I wanted to show you maybe last couple things you have, but you can also let's maybe go back to the schematic here, because so there's blocks here 1, 2, 3. The sinks allow you to basically take the signal wherever you want in the system, so for example inside one of these blocks here you'll find, for example, the sinks. In this case they are deactivated, but they allow you to actually get access to waveforms and signals wherever you want in the system. So this is one of those outputs here, and you see this is a simple picture. You see that this is the FFT output, and you see that it is a comparison between the case of 1 channel versus 4 channel, and you see the signal to noise enhancement due to using multiple TX as opposed to this 1 TX curve here and dashed. And you can directly see the improvement at the very fundamental level. You can basically visualize, easily visualize every sample that is generated in any part of the system there. What we have just seen in the example is the possibility of using Matlab as a modeling language or tool inside Systemvue. Now we're looking at the other possibility, which is using Systemvue as an RF and a radar environment modeling tool from within Matlab. So what you see here is it's a simplified chain, similar to what we've seen before, is a single channel input, output, or TX-RX. It's essentially doing the same things in a simplified way. We have a TX modeling here. We have some simplified targets, some noise density. We have RX, the RX front end model. You see here the A to D converter, and then all the way to the end of the chain here with some signal processing. So what and then you see here at the end in this red circle, and it's highlighted here. In this case, it's a radar where we do some MTD processing, but this block here that you see here allows it's actually building a data cube, and all this structure here can be directly controlled from Matlab. So you see the Matlab window here, and basically what we're doing is passing. We can pass parameters, and you see here those are we can now visualize the whole code, but essentially we point to the Systemvue workspace. We pass parameters. We activate an analysis where we run the analysis directly from Matlab, and then we get the data directly into Matlab from Systemvue. In this case, Systemvue, once the setup is defined and saved, then it runs basically it runs in the background and is directly controlled from Matlab, and then you can go ahead and then make your measurements in Matlab as you see here, and that is also it's a mode of use that it's let's say is more directed to people who are signal processing specialists. So another important point is once you define the system as we've seen, you may want to use that system description to generate complex signals for testing actual the modules, and you can do this for receiver tests or transmitter tests. And the way you do it is you can use Systemvue to drive directly for example, a wideband arbitrary waveform generator like this one. It's an M8195 from Keysight, which in its turn then it's driving a microwave source. And then through up converter, filter, attenuator goes to the TX antenna, and that's used. This signal can be used for receiver test, and then for transmitter test, same thing. You can get the signal out of the module here into an antenna, and then into a down converter, goes into a signal analyzer, and then the wideband signal is then analyzed on a scope, on a wideband scope here. And in this case, what you can do is, yes, you can use this block for the M8195 to drive, as you see here, with an IP address, directly point to the AWG, and then create the complex signal that we've seen before. You can directly you can synthesize it in an actual electrical signal. And similarly, on the analysis side, you can use the VSA, which is software that runs both on the spectrum analyzer, signal analyzer, and in Systemvue to do complex signal analysis in Systemvue or directly on the signal analyzer. Let's now go into the last part of the presentation and take a quick look at the higher level modeling, which I call here vehicle level modeling, that you can do in Systemvue. Let's now go through the last demo of this session. So what you see here is a system that's similar to the one we just saw in the previous example. So it's slightly simplified. There's TX here, RX here. There's signal processing down here. The part that is most interesting here is this Mrt Channel Modeling part. And there's a block here that I'll just go in real quickly. As you see here, it points to a file, and I'll show you where that file comes from. And here you have antenna configuration. So you can specify TX and RX antenna position and pattern, similar to what we've seen before. Now the part that it's interesting here is where this file comes from, which is it defines the channel that links the TX and RX. So basically the radar environment. So I'm going to open a second window here. And this is the ray tracing scenario editor that is included in Systemvue. And as you see here, it allows you, it has a library of objects, so car, truck, bus, road, radar, static targets, and there's also possibility of entering user-defined models or objects. And so, for example, in the car, you see there's a standard, which means low resolution. There's mid-resolution, high-resolution car, and same for truck. Different possibilities. Bus. Then you have road, etc. So you can basically arrange, and then yeah, static targets. You see the different possibilities with the road signs, guardrail, lampposts, buildings, etc. You can build this sort of scenarios, and for each object here you specify the position and the type of motion, etc. You also define other system parameters down here, like let me make this a little bigger so you can see here the frequency, then you can see start and stop time, type of polarization. You need to find the field of view also, and this is also important, is the ray setting, which is the density and how many bounces are calculated. So without getting into more details, you defined the scenario and both the static and dynamic characteristics. You can do a preview. Now in this case we'll run it for a quite long period of time just to make sure that the motion are actually defined correctly. And then once this is done, you hit this calculate button, and that's where the rays are calculated, and essentially the channel characteristics or the channel behavior is calculated based on the parameters described here. And then at this point you go back, and this block points to this file here. They're generated in the previous simulation, and you run the high-level simulation here at the system level, and you get results like you get results like for example a range Doppler map. So this is what you see here. It's a range. You have velocity here, range here, and you have this is a range Doppler map. You can go 3D if you want, but allows you to have a quite descriptive range Doppler configuration or result here, much more detailed than you will get with let's say the simulation we've seen in the previous example. We are now at the end of the session, so just to summarize the main contributions of Systemvue to automotive radar system design. So we've seen how we can simulate or model and simulate the RF and microwave parts of the system, the analog high frequency TXRX. The antenna modeling, also how we have access to radar signal processing algorithms in the automotive radar library, also how we can add models in Matlab, but also C++. We haven't seen this, but it's a possibility. So the interface to the C++ interface into Systemvue is open and documented. We quickly took a look at links, how to link to test equipment, and last but not least, how to define the radar environment in different levels. We've seen the first, let's say, detailed but still discrete type description of the targets, and then we switched to a more higher resolution radar environment definition in the last example and demo. So that's the end of.
Okay, thanks, Ricardo. Okay, Ricardo, here is your first question. Jonathan asks, what about measurements or other model data? Can I import S parameters or nonlinear models into Systemvue?
Yep. So it's definitely possible to import S parameters for linear data. Now, for nonlinear data or circuit data coming from circuit simulation or from measurements, there's at least a couple of options. It's actually more, but the two main options are X parameters. which is a format that is supported by our circuit simulators and also our network analyzers. And there's also a format called FCE, Fast Circuit Envelope, that is coming from our circuit simulators. So these are the main options. We can also import AM, PM data for amplifiers and things like that, but for the moment I'll leave it at that.
Okay, great. Thanks. Here's your next question. This one comes from Carrie. She asks, if my circuit designers use ADS, can I co-simulate with both tools?
Yep, and so ADS is Advanced Design System, another product from Keysight, and it's used by circuit simulators for RF and microwave circuits mostly. And it is possible to use circuits designed in ADS in co-simulation, and that's another possibility as well, to simulate or to include into the system level simulation both linear and nonlinear models from circuit simulations. It's a nice complement to the previous questions. It's a previous question.
Oh, great. Okay, here is your next question from Tomas. He asks, what kind of computer do I need in order to use Systemvue? Does it take a lot of memory or processing power?
Yep, it's a good question. So it depends really on what you're doing with Systemvue. Some of the things we've shown today do not require a large amount of processing data. So a regular, normal, laptop or desktop PC is going to do just fine. Some tasks, however, take more computing power. So something, for example, that we've seen that can use as much processing power as you have to speed things up is MIMO type structures where you have parallel channels, and so that takes advantage of parallel computing. Another one is the ray tracing software that I've shown towards the end of the demo, and that also can use additional processing power if available in the way of multiple cores or larger number of cores. In terms of memory consumption, it's actually dependent on the amount of data that is generated by the simulation. So typically, what we do during the debug phase of the system design or the modeling of the system with Systemvue is we actually extract quite a bit of data to actually check that the simulation is producing reasonable results. But then, as soon as that verification phase is done, then basically it's highly recommended to reduce the number of, or to just extract the data that is necessary, and that reduces memory consumption.
Okay, great, thanks. Okay, Ricardo, here's your next question. Luke asks, does Systemvue run on Linux? Okay,
so today Systemvue only runs on Windows platform. However, being it part of the Pathwave software family, longer term, it's going to work also on Linux. But that is something that's going to happen at some point in the future. So stay tuned, and keep your fingers crossed.
We will. Okay, here's your next question from James. He asked, do you provide verification examples for the ray tracing software you mentioned?
Yes, so that's a very important topic. I always get that question from customers. So the first step to start using the software is to do some basic verification. I think a sphere is a classic case, just to make sure that the power returned is correct for the shape and the distance of so for the size and the distance of the sphere. So that we do have some examples that show that. I think we have currently in our. I was checking in the latest beta versions, we have actually the near field and the far field verification for that case, and also application engineers like myself help customers go through that basic verification phase, kind of stage of the tool, and so whatever configuration is useful to do that verification, that we can help the new user to set it up in the system and verify that they're getting the right answers.
Great, thank you. Okay, Ricardo, here is your last question. This one comes from Kendall. Can I include antenna radiation patterns from 3D EM simulators like Hfss or CST?
Okay, yes, so this applies to the part where we look at the modeling and MIMO, complete MIMO system, and right now I forgot if I showed that part in detail, but essentially there's a pull-down menu where for each antenna of the MIMO system, we can point to a radiation pattern for each element, or also we can use the same pattern for all elements. In any case, there are 3 EM simulators that are currently supported. One is EM Pro from Keysight, and then there's the two simulators you mentioned, so Hfss from Ansys, and it's actually Micro Studio from CST. But underneath, there's a possibility of importing pattern files in CSV format, so in ASCII format, and so pretty much any radiation pattern can be formatted to be input or to be used by Systemvue for that. For simulating the antenna response and also the complete system behavior. So I guess I'll hand it back to you, Carmina. Thanks all for your help today.
Thank you again for attending Challenges and Solutions of Advanced Automotive Radar System Design, brought to you by Keysight Technologies. Please visit us at www.keysight.com/find/events for a list of upcoming events. Thanks and stay well.